Welcome to Digital Learning at OS Style, everyone. Today's learning target is identify the first difference, second difference, or common multiplication pattern so we can determine if a table of values is linear, quadratic, or exponential. So we've already looked at equations and their degrees or variable location to determine if they represented a function that was linear, quadratic, or exponential. And today we're going to learn how to do that from a table of values. So I've given you a quick note summary that should help us when looking at our table of values. If it's linear, you'll never see the same y value twice. And there's something called a difference, and we'll talk about that more in just a minute. The first differences will be the same if the function is linear. If it's quadratic, you can see the same y value more than once. That quadratic pattern, when the graph, the parabola turns around, you can see y values repeat. And something called the second differences will be the same if the function is quadratic. And for our exponential, you're going to see in an exponential table of values, the y value is going to change a lot quicker than the x values. You'll never see the same y value twice, and you're going to find this common multiplication pattern. So these are the three things we need to keep in mind while we're looking at each table. So what is a difference? Because I mentioned them in the linear and the quadratic. So the difference is when we're looking at our y values, we want to see how are they different from each other. So when I look from -2 to +1, if I add 3 to -2, I'll get +1. So that's a difference. Let's see what the difference is from 1 to 4. Well, if I add 3 to 1, I'll get 4. There's a difference. How do I get from 4 to 7? Well, if I add 3, 4 plus 3 is 7. And if I take 7 plus 3, I'll get 10. If you take a look, all of these differences are the same. It's the first time I looked at their difference. This is called the first difference. Now, let's take a look. If the first differences are all the same number, go back and look up here. Does that match any of these? It matches our linear. First differences are the same. That means this table of values is linear. And that's how we're going to identify each one of these. So let's take a look at our second one. Remember, we're only looking at our y values. So -6 to -6, there is no difference. So I would add 0 to that. How about -6 to -4? If I add 2, -6 plus 2 is -4. Okay? Well, the first differences are so far not the same, so it definitely is not linear. So let's see what else is going to happen. How do I get from -4 to 0? If I add 4, -4 plus 4 is 0. And how do I get from 0 to 6? 0 plus 6 is 6. All right, so my first level differences here are not the same. This is definitely not linear. Another way I could have told that before I even started is I'm seeing a y value repeat. So it can't be linear and it can't be exponential because neither one of those have a y value repeat. It could be quadratic. Let's take a look because the quadratic, refresh your memory, has said something that said the second differences are the same. So what that means is here we have our first differences. Now what's the difference on our first difference? To get from 0 to 2, I would add 2. To get from 2 to 4, I would also add 2. To get from 4 to 6, I would also add 2. That's the second time I looked at differences, so that's the second difference. All of those second differences are the same, so that makes this quadratic. Okay. So we got a linear and we got a quadratic. Let's take a look at our last one. We've got some decimals here. And I know we don't like decimals. We don't like fractions. So what I'm going to actually do is I'm going to kind of ignore these guys right now. And I'm just going to look at these three and see if I can identify a pattern here. And then just make sure that it holds true for these beginning two guys. So I can either, how can I get from 2 to 10? I could add 8. But then I'd have to add 40 here. That doesn't look like it's going to be. It's definitely the first differences are not the same. And I don't have enough information here to tell about the second differences. But if I look, 2 times 5 is 10, and 10 times 5 is 50. I wonder, does that pattern hold through for all of these? So I'm going to take my calculator, and so I'm going to look back here. Is 0.08 times 5 is 0.4. Okay, so that holds true. I multiplied there. What is 0.4 times 5? It is 2. Here's our pattern. Each time I multiplied by 5 to get between all of our numbers. We go back to our note summary. It says there's a common multiplication pattern with an exponential. So because I'm multiplying by the same number each time, that makes this table of values exponential. Okay. All right, let's try a few more of these. On the front, I had my tables going horizontally, but sometimes you see them vertically too. So I wanted you to have the chance to see them both ways. Again, we're going to look at our y values and how they're changing, because that's what's important in identifying the function. So we're going to look -5 to -4. Well, if I add 1, I'll get that. -4 to -1, I would have to add 3. Okay, so my first differences are not the same. -1 to 4 would be add 5, and 4 to 11 would be add 7. So that first level of differences are not the same, so it's definitely not linear. Let's look at the second level. 1 to 3 is an add 2. 3 to 5 is an add 2. And 5 to 7 is an add 2. The second level is the same. That's going to make this a quadratic. If I look at this table, I see a pattern that emerged, and you might not have seen it yet, but let's just take a look. This is +2. No, it's not. It's -2. This is -4. This is -8. This is -16 to get between those numbers. First differences are not the same. Let's check again. I have the same numbers. This is -2, -4, -8, -16. So our second differences are not the same. So it's not linear, it's not quadratic, so my last choice is exponential. Do I have a common multiplication pattern? If I multiply each of these by 2, it works. So that's going to make this one exponential. Okay, let's do just a couple more. That way you have plenty to go back and look over along the way. 5 to 9, that's an add 4. 9 to 13 is add 4 again. 13 to 17, add 4. And 17 to 21. Every single one of those has the same difference the first time through. That makes it linear. I like the linears, they're the fastest so far. Okay, let's take a look at our middle guy. Remember, we're only looking at the y values. How are they changing? So here I'm going to subtract 1. 0 minus 1 is -1. -1 to 0 is add 1. 0 to 3 is add 3. And 3 to 8, I'd have to add 5. So clearly my first differences are not the same. So what's the difference of the difference? -1 to 1 would be add 2. 1 to 3 is add 2. Line. That's going to make this table quadratic because the second differences are the same. Now for our final table, let's take a look. 3 to 9 would have to be add 6. 9 to 27 is add 18. 27 to 81. Boy, those are changing pretty quickly right there. When I see this big change, I got to think multiplication. So I'm going to look for a multiplication pattern. What times 3 gives me 9? Well, if I multiply by 3, is 9 times 3 27? It is. 27 times 3 is 81, and 81 times 3 is 243. So that makes this table exponential. Right, you have an assignment on Canvas that uses these notes. Refer to these notes, come back and listen to the video if you need to, and be sure to email if you have any questions. Talk to you later.